Hello everyone, my name is Franco Pucci and I am the technical consultant for the STS Association. I have been involved in the prepayment industry for over 25 years. Welcome to the STS training video series where we will explore all aspects of STS and the STS standard. I hope you find these videos helpful. In this video we will deal with section 5.4 and 7.1 of the IEC 62055-41 edition 3 document, token processing. If we have a look at the STS meter data flow reference model in 5.4, you'll see that there's essentially a flow that goes from the token carrier through the connector to the token carrier data unit, the application process data unit, and then the meter application process. So what happens is the token is presented to from the token carrier to the connector through to the TCDU. The token is read, and at this point you have a chance to do any correction you want to. For example, if you typed an incorrect digit into the keypad, you can correct it. It goes through to the TCDU. The token data gets extracted from your token or from the keypad entry, and the token is decrypted at this point, and an authentication result and a validation result are calculated. They're also sent forward to the APDU as well as backwards to the TCDU, or to the interface to the TCDU. The token is processed, it's extracted, and the token is sent through the APDU to the meter application process. This then, along with the authentication and validation result, will process the token, and it'll come back with a token result. Now, if the token is authentic and valid, it'll go through. If it's not authentic or not valid, it's a different token result that comes up. But we'll discuss these token results a little bit later. Then the token may be erased if the token is accepted. If it's not accepted, nothing's done to it. But token erasure can take place. This can either be via saving the TID into the TID stack of the meter if it's a keypad token, or by erasing the magnetic strip on the card. In some cases, some meters support a token lockout, specifically on the virtual token carrier port, because data entry is a lot quicker on that port. What happens then is the token lockout comes into play if you have an authentication result that's not authentic or not valid, or the token is not accepted, and it will time out and then only allow you to enter the second token a little while later, and this time can increase with each incorrect token that you put in. Then if the token is cancelled because it's been accepted, then the token could be written, or an answer could be written back into the token. For example, if you're using a smart card, or if it's a virtual token carrier port, and the result could be sent back as well if you have a two-way system. And this obviously is specific to each token carrier type that is used. Now let's look at the transaction reference numbers used in the STS. So you have a 66-bit token data presented to the APDU. The authentication result is a status indicator to tell the meter application process if initial authentication checks have passed or failed. And if you have a look at what's contained in the authentication result, the value can either be authentic. This is false if any of the below error codes is indicated, and it's true if none of the below error codes is indicated. First one being CRC error, where the CRC value of the token is different to the CRC value as calculated from the data in the token. So with the token, you get a CRC value at the end of the token, the last 16 bits. The meter will take the token that is entered, it will decrypt it, then calculate its own CRC value. If those two match, then it's okay, and if they don't, you end up with a CRC error. If there's a manufacturer code error, for example, in a class 1 token does not match the manufacturer code for the decoder or the meter, then this gives you a manufacturer code error. If either of these two come up, then the token is not authentic. If the authentication tests have passed, it moves on to the next stage, which is the validation result. This is a status indicator to tell the meter application process if initial validation checks have passed or failed. Okay, so the token is valid if none of the below error codes is indicated, and not valid or false if any one of the below error codes is indicated. The error codes could be old error, where the TID value in the token is older than the oldest value in the TID memory store of the payment meter. So the meter stores up to 50 or maybe more TID values, and if the TID value is older than the oldest one in that memory, then it's seen as old. If the TID value in the token is already recorded in the TID memory, that means the token has already been used, then it will come up as a used error. If the TID value in the token is larger than the key expiry number stored in the payment meter, then it means that the key has expired and the meter is not allowed to accept it. And then you have a DDTK error. If the decoder has a DDTK value in its decoder key register and a transfer credit token is presented, then you will land up with a DDTK error because you cannot vend credit to a meter if it's coded with a DDTK. So now authentication tests have passed, let's assume that, and validation tests have passed. Now you'll end up with a token result which is calculated. And this is the result of the processing of the token by the meter application process. So it's done all the initial bits, it sends everything, it says it's happy with the token, please process it and give us a result. The results can be accept if the token was successfully processed, and it will be not accept or false if any one of the below codes is indicated. And my apologies. False if one of the below error codes is indicated. First, it can come up with the first KCT. The meter application process indicates that this is a set first section decoder key. Then the token is provisionally accepted only. Second KCT can come up if it's the second token of a key change set, and this token is also provisionally accepted, and also for the third KCT and the fourth KCT. If you get an overflow error, obviously then it will be rejected as a non-valid token, where the credit register in the meter would overflow if the token were to be accepted. Then the token is in fact not accepted, and your result will come back as overflow error. If there's a key type error, in other words, you're trying to do a key change from a key type that is allowed to a key type that is not allowed, then it'll come back with a key type error. A format error, one or more of the data elements in the token doesn't comply with the required format for that element, then a format error will result. A range error, if one or more of the data elements have a value that is outside the defined range of values defined in the application for that element. Okay, and then obviously a function error. A particular function to execute a token is not available. For example, you trying to put a water credit token into electricity meter, that would result in a function error. So let's look at some examples of token processing. You have a key type error. This could be attempting to change from a DUTK to a DITK. That is not allowed, as we have seen in a previous video. So that results in a key type error. A format error, an alpha character is assigned to a decimal value, maybe. Or a range error, a value of 0 is assigned to the key revision number when the allowed range is from 1 to 9, not from 0 to 9. And function error, a water credit token is entered into an electricity meter. A few things to note: key change tokens may be entered in any order, so you can put token 3, then 2, then 1. Messages may be displayed in any language or icon. Although the message itself must be the same, in other words, the meaning of the message, you can put it in icons or you can put it in any language, as long as your meter manual obviously explains what these mean, and obviously it is part of a contract where the user or the utility says, I want my messages to be in a particular language. You may do so. After a key change timeout, which is between 3 and 10 minutes, the key change process must terminate. Okay, this is in case you, for example, go off somewhere after entering the first key change tokens and you forget to do the second one. After 10 minutes, that whole process times out and you have to start again from the beginning. Token lockout is an optional function, and it usually is only employed on the virtual token carrier port. The acceptance rate of a token using a keypad is a lot lower than on the BTC port. Also remember that up to 2 invalid tokens may be entered between any valid key change tokens. That's just in case you make a mistake while typing. So let's look at the process then. You get the 66-bit token from the token carrier data unit. You extract the 2 class bits, and we'll explain why we do this a little later. Decrypt using the 64 or 128-bit key, and that key is the key that resides inside the meter, and then you use whatever decryption algorithm is programmed into the meter. You restore the 2 class bits. After doing that, you authenticate and stop if not authentic. The authentication results goes off to the APDU. Validate and stop if not valid, and the validation result goes through to the APDU as well. Process the token data in the APDU and then return the result from the APDU. And then if you have a magnetic card and the token result says accept, then you can cancel the token, and in the case of a magnetic card, you erase the token strip. So why do we do this class bit extraction? Well, class bits are not encrypted so that the meter can recognize the token class without having to decrypt the token. The conversion from binary to 20-digit would have a static first digit if the transposition is not done, since bits 64 and 65 would be static for a particular class of token. So we take bits 64 and 65 and move them into positions 27 and 28, so that the first digit of the resulting 20-digit token is not static for any particular class. So it's simply just another layer of abstraction for the 20 digits. Let's look at the token rules. A token is cancelled by storing the TID value into non-volatile TID memory and or erasing the magnetic card for token carrier 02 types. The meter will store at least 50 TID values in its TID memory, which is non-volatile. The smallest TID value is erased when the stack is full and a token is accepted. Okay, in other words, the one that was entered right at the beginning. Okay. The TID memory is not affected when a key change token is accepted, and that's because a key change token does not have a TID inside it. So only tokens with a TID are written into this TID stack. At the time of manufacture, a manufacturer must fill the TID stack with the date of manufacture or repair of the meter. The meter must not accept any token that has a TID value prior to the date of manufacture. And a meter must accept tokens when in a power limiting or tampered state, and this could be part of a contract. Let's continue with the token rules. Key change tokens are only executed when the complete set is accepted. So do not start changing your meter key until all the tokens have come in on a key change set and all the tokens have been verified and are accepted. Only then do you change the meter key. Only the last accepted token in a key change set indicates accept. The others will say first KCT or second KCT or whatever the case is. On the last one, let's assume the last one happens to be the fourth key change token for an EA11 meter. On the fourth one, you will not display fourth KCT, you will display accept if the fourth one is the last one going in. The token is only accepted if authentication and validation are successful. Okay, it's a sequential thing, so you do authentication first, then validation. If all that is successful and you don't have a function error or any other error, then only is the token accepted. If a credit overflow would be caused by a credit token, the token must be rejected. Obviously, this token is then not written into the TID stack at all. Key change tokens may be entered in any order, either first one second or the second one first. Up to 2 invalid tokens may be entered during a key change operation. I've mentioned that already. And the key change operation must time out between 3 and 10 minutes if it has not been completed. Okay, a further few rules. A meter must uniquely display acceptance of a token, rejection of a token, when a token is old, when a token is used or duplicate, when the decoder key has expired, when a token is presented to a DDTK coded meter and is not allowed to accept it, after a successful key change operation, and if there's a credit overflow condition. Then whether you use icons or language to explain all of these, they must all be present in one form or another. If the meter application cannot execute a token, you also need to display a message of some type. Display indicators may be of any type or language, but must be stated in the sale agreement with your customer. The Drn and EA must be displayed on a visible part of the meter once installed. And that's important to note, please. Don't put it on the back of a meter, install it, and then you can't see it. For a split meter, it must be possible to determine the Drn and EA from the customer interface unit either by a button press, a shortcode, or the entry of a test display token. Token entry results must be displayed on the device where the token was entered. So it's pointless having a CIU, you enter a 20-digit token, and the meter sitting on top of a pole has a display and it shows the message. I think we've said enough about the 6205541 specification. For more information, please see the specification itself. You can order one from the IEC web store. In the next few videos, we will have some fun with simulators. This brings us to the end of this video, this part of the video series. I hope you found this video helpful, and I hope you'll join us for the rest of the series. Goodbye and see you again soon.